So in this next section, we're going to be talking about how the properties of elements vary in a systematic or periodic fashion as we move across the periodic table. There's going to be three properties that we'll be looking at. There's the atomic or ionic radii, which is a measure of the size of the atoms. We have the ionization energy and the electron affinity. So what we would expect is, because the configuration of electrons in atoms varies in a periodic systematic fashion as we move left to right, top to bottom across the periodic table, we would expect that many properties of elements would also vary in a systematic or periodic fashion. The first property that we're going to be looking at is atomic size, and it is important to recognize that atoms are not hard spheres. Typically, we'll determine the diameter of an atom by measuring how far away it is from a neighboring atom in either a sample of the element or of that atom in a compound. You might see some different sizes for these atoms recorded depending on how those values have been determined, but the general trends remain. So the first trend that's kind of obvious is that as we go down a period, the atoms get bigger. And it's important to consider what's happening as we go down the period. Every time we move down one row, we are increasing the value for the highest value of the principal quantum number by 1. So moving down the rows of the periodic table, what it represents is adding another layer of electrons. So it's like adding layers to an onion. So it is not surprising that as we move down a column, the atoms get bigger. As we move across a row, we're adding electrons to the same layer. So the electrons are going in at approximately the same distance from the nucleus. So we might expect that the atoms as we move across a row would be exactly the same size. But as we add every electron, we're also doing something else. We're adding another proton. So as we move across, we're adding more protons to the nucleus, and we're adding electrons to the same layer of electrons. What happens is, as we add more protons, it causes every layer of electrons to get pulled in a little bit because we're increasing that positive nuclear charge. And the net result of this, what we see is, as we move across a period, is we get a modest decrease in atomic radii. So if you put both those trends together, a decrease in size as you move across, an increase in size as you move down, we can draw a diagonal arrow like that, and that is how we see an increase in the size of the atoms. So a typical questions concerning this will be ranking. So this says rank the following atoms in order of increasing atomic radii. So the first thing that I want to do is identify the smallest one, because I want to list these from smallest to biggest. So it's not too bad. I just have to think about where these 4 atom types fall on the periodic table. Sodium is element number 11. Potassium is element number 19. It's in the row below sodium, so potassium is going to be bigger than sodium. Chlorine is in the same row as sodium, but it's way over on the right. And then argon is also in the same row as sodium and chlorine, but it's a little further over to the right. So remember that the smallest atoms are up here and the biggest are down here. We can pretty easily identify that the smallest atom of this group is going to have to be argon, and then the biggest atom of this group will be potassium. And then as we move towards the left in this third row here, what we're going to do is we're going to be getting bigger and bigger. So it's going to go chlorine and then sodium. And if we want to get really fancy, we can put some symbols in here. Argon is smaller than chlorine. Chlorine is smaller than sodium. sodium is smaller than potassium. You always want to make it clear how you're ranking things in a ranking problem, just in case you get the order reversed, and then you can at least get some partial credit for demonstrating that you knew the concept. So, similar to atomic radii is ionic radii, and ionic radii is determined by measuring the distance between one ion and another ion in an ionic crystalline compound. And this is going to be important later on. We're going to be talking a lot about crystalline ionic compounds and their chemical structure. So what we find is the following general trends. Cations are typically or always are going to be smaller than the atoms that they are made from. And that makes sense because when you form a cation, you lose electrons. And anions are always larger than the atoms that they're made from. And that makes sense because in order to make an anion, you have to gain some electrons. The other thing that we find is that ionic size increases down a group just like atomic size. So as we head down a group of ions, whether they are cations or whether they are anions, they get bigger. Okay, so that's kind of pretty simple. When I look across a series of cations, they get smaller. Every time they get smaller, they get smaller. When I look across a series of anions, they also get smaller. But what we see is that in any given period, the anions are always bigger than the cations. So it's kind of like there's two series. They follow the same rules as what we saw for the neutral atoms, except for the anions are kind of doing their own thing and the cations are kind of doing their own thing. So ionic radii does decrease as we go across for a series of cations, and it does decrease as we go across for a series of anions, and it increases as we go down for both anions and cations, but in any one row, the anions are always bigger than the cations. So it's a little bit confusing, but it's quite logical. So that concludes the section on the first periodic property that we were talking about, which was atomic and ionic radii. And now we start talking about this thing called ionization energy that's often abbreviated IE. And so what the ionization energy is the energy required to remove a mole of electrons from a mole of atoms that are in the gas phase. And we're going to come back to this later on when we start talking about what's called Born-Haber cycles. So this is an important concept to get a handle on right now. So we can remove more than one electron from an atom. The first electron that we remove, the energy to do that process is called the first ionization energy, and we can indicate that it's the first ionization energy by putting a 1 there. And that's going to remove the very outermost electron. So we take our gas phase atom, we remove 1 electron, gives us our single positive gas phase ion and our electron. And the energy involved in that process is called IE1. We can remove more electrons, so we can remove a second electron. So we take our ion with its single positive charge and we remove a second electron, giving us a double positive charge. And the energy required to do this is called IE2. And so on and so forth, we can keep removing electrons. What you'll find is that the second electron is because it's being removed from a positively charged cation, it's always going to be more difficult to remove than the first. That is, IE2 will always be greater than IE1. And if we removed more and more electrons, that would be the case. So IE3 will always take more energy than IE2, which will always take more energy than IE1. And if you're going to remove even more electrons, that would take more energy because that positive charge just keeps building up and up and up. So how does IE1 vary across the periodic table? And it's a pretty simple rule. As atomic size decreases, the energy required to remove that first electron increases. And why is that? Because that electron is going to be closer to the nucleus and therefore held more strongly. So it is easy to remove an electron from a big atom and hard to remove an electron from a small atom. So as a result, we had increasing size, but what we will have is decreasing IE1. So it follows the same trend, so it's pretty easy to remember. So what we would expect is as we move across a period, it's going to become more challenging to remove an electron, but as we go down a group, it's going to become easier. So if I look at moving across the second period here, so that's going from lithium and ending up at neon, you can see that it becomes more difficult as I move across. If I look, so that's going across the second period, and we see going across the third period, we see the same trend. If I look at going down a group, and a good example of this would be heading down group 1A, so lithium, sodium, potassium, rubidium, cesium, you can see that IE1 is decreasing as we go down a group. So decreasing as we're going down a group and increasing as we're going across a period. So that all makes sense. But what we do see is a couple of sort of consistent lumps and bumps. And this guy here looks like it's too high. And this one here looks like it's too high. It's not following the trend. The same here. This one is too high. And this one is too high. So we see a couple of, interesting trends, and the question becomes, can we, or where there's sort of exceptions, can we explain these things? Well, one thing that we know from the quantum theory is that electrons in an S subshell, they have this quality called penetration. They spend some time very, very close to the nucleus, because we have this little peak right here. And electrons that are in 2p's don't do that. So electrons that are in the 2s are going to be really, really hard to remove compared to electrons that are in a 2p. So electrons in a 2s might be harder to remove than what we would intuitively expect. And so we see that here, these guys here, which are S electrons, are more difficult to remove than p electrons that are in the same shell. They're just kind of like unexpectedly tough. That doesn't really correlate exactly with with relating everything to being ionic size. We have to consider the orbital penetration as well, where we get this little bit in here in order to explain the complete trend. And so the fact that we just can't explain everything on the basis of atomic radii or atomic size, this is powerful evidence that the quantum theory is working. Now, the other thing that we will see was that second exception, and we'll talk about that now, is what it is related to these guys here, again, being unexpectedly tougher to remove than what we might intuitively expect. So what we find is that a half-filled P subshell, which are these elements in here, have P3 electron configuration. That's really, really tough to break up. A half-filled P subshell is very favorable. So what we find is that this doesn't want to get disrupted, and also it's really easy to form a P3 from a P4, so this is kind of really easy to remove one electron from those elements that come after P3. So this guy is kind of like very tough to break up, This guy kind of doesn't really mind forming a P3 from a P4. It doesn't mind losing an electron and getting this stable configuration. So the net trend is that the ones that are in the third position in the P block, they're kind of unusually stable and quite easy to form. So we mentioned this idea earlier that successive ionization energies increase. So, maybe I'm going to lose 5 electrons. That's going to be harder to do than losing the 4th electron, which will be harder to do than removing the 3rd electron, which will be harder than removing the 2nd one, which will be harder than removing the 1st one. And that makes sense because it becomes harder and harder to remove an electron from a more positively charged species. What we find, though, is if we look at a series of ionization energies, we observe that once you remove all of those valence electrons, those ones that are in the outermost shell, then you get a really, really big jump in ionization energy, bigger than what you might expect. And the reason is, at this point, what you're doing is you're breaking up that core electron configuration. You're destroying that very stable noble gas configuration. And this can be a useful mechanism for identifying how many valence electrons an element has. So I'll show you now. So sodium is in group 1A and has 1 valence electron. If we look at the difference in ionization energy between IE1 and IE2, you see that it's huge. It's bigger than any of the other differences. Sure, all of these guys do increase, but there's a massive jump right there. And that tells us that sodium has 1 valence electron. When I move on to magnesium, we get this kind of steady increase of around about 700 kilojoules per mole when I move from IE1 to IE2, and then there's this massive jump over 6,000 kilojoules, and then there's kind of like a fairly steady difference in energy between subsequent ionization energies. So this tells us that magnesium has 2 valence electrons. If I go to phosphorus, I get this like modest increase in ionization energy as I go from IE1 to IE2 to IE3 to IE4 to IE5, and then there's this huge jump between IE5 and IE6, and that lets us know that phosphorus has 5 valence electrons. So that's how we can tell by looking at ionization energies how many valence electrons an atom has. Now, it's worth noting that in chemical processes, because these energies to remove these core electrons are so big, chemical reactions are not capable of removing core electrons. We have to do other stuff to make that happen. So our final property that we're going to look at is called electron affinity, often given the symbol EA. And it's the energy change when 1 mole of electrons is added to 1 mole of atoms, again, in the gas phase. So we take our neutral atom, we add an electron, and we form an anion. Now, because we're forming a bond here between the electron and the atom, we're going to have energy being released. Energy is released when bonds are formed. Energy is taken in when bonds are broken. So generally, energy is released when you add an electron to an atom. Why does the electron stick? It's due to the result of the attraction of the electron to the nucleus. So again, we can kind of do the same numbering. Adding the first electron is called EA1. Adding the second electron would be EA2. Now, the pattern of electron affinities is more variable than either atomic size or ionization energy, but the general trend is that it increases from the bottom left of the periodic table towards the top right of the periodic table. So it's on the same arrow that the other periodic properties are on. Okay, so that concludes this section. I would encourage you to work through these problems. A good time to do that is on Wednesday at our question and answer session.